and today I'll be talking to you about enhancing Java applications for the cloud. So the necessary disclaimers. All right, so a bit about myself. I'm a software developer on the OpenJ9 VM team. I've been working on JVMs since the Java 7 timeframe. So I've worked on a few features in the past. So runtime support for Lambda expressions, modularity, etc. Right now, the main things I focus on are leveraging checkpoint restore capabilities in the JVM, and also collaborate with some other developers on the Valhalla experts group. Okay, so in today's talk, I'd like to discuss some of the challenges of deploying to the cloud. Specifically, what are the costs in doing so? A lot of people are going under a modernization journey where they're taking their monolith and moving it to the cloud. So today we'll look at some of the costs that are associated with this. Now, there's many different types of costs. There's the cost of modernizing your workflow, updating your tools, changing your developer workflow so that it's a seamless experience for them. But in this talk, the focus is on the computing costs of deploying to the cloud. So we will look at how to minimize those costs, and we will see how improving startup time and density helps to minimize those costs. So we're going to focus on minimizing costs for JVM-based app servers. So this is a JVM-centric talk. So, in the last 10 years, it's becoming an increasing trend to deploy your application to the cloud. In many cases, people are using public clouds like Azure, EC2, Google Cloud, etc. A lot of people want to do either a full public or, a hybrid solution on-prem and public. And it's because there's many benefits of doing so. When you deploy to the cloud, you're not limited by the number of machines you have. You can scale as your demand increases. So there's a lot more flexibility when you deploy to the cloud. Also, it decouples the task of maintaining hardware so that your developers can focus on, writing the applications, doing what they do best, and they don't have to focus as much on IT infrastructure. So in some cases, this can help boost developer productivity. So basically, the more you do in the cloud, the less you have to do on your own. At least that's the theory. So for the most part, people who undertake this transformation are happy with the choice they've made. So the main costs that cloud vendors incur are networking, storage, and compute. So networking costs include the cost of, setting up the network, buying the components, maintaining it. Likewise with storage costs, buying the disks, maintaining it. Compute costs are similar. You have to buy the machines, CPU, RAM, and then the power for operating it. And then it may also include licensing costs depending on the OSs that you make available. So cloud vendors factor in these costs when determining what to charge consumers. And the compute cost is what we're going to focus on today. So most cloud vendors offer a pay-as-you-go type of pricing model, basically where you pay for your compute capacity for a certain duration of time. So AWS, for example, has duration pricing or on-demand pricing. And so you request a certain number of vCPUs and amount of memory, and then you're charged based on your usage of these resources. So how do we save in the cloud? So as we saw in the previous cloud, the main cost from a compute perspective is the number of CPU you're using and the amount of memory you're using, multiplied by the amount of time you're using it for. So for most applications that live on the cloud, demand isn't constant. It varies over time. Perhaps it's higher certain times of the day than others, maybe certain days of the week, certain weeks of the month, etc. If you have a web store, for example, it might be higher when you have a sale and lower off-season, or if, like Black Friday might be a very busy time. So the demand varies. It ebbs and flows. So using a deployment strategy that can dynamically scale with demand is very important to saving resources. So this can be done with scale to zero strategies. So scale up when demand goes up, scale down when it goes down, scale to zero when there's no demand. And a lot of people are adopting this approach. Technologies like Knative, OpenFaaS have support for this. Another way to reduce costs, is when you are running, is to increase the density. Essentially, do as much as you can with as few resources as possible. So if you can use less memory, less CPU to achieve the same goals, then clearly that's a better way of doing things. And it's far more economical. So what needs to be done to save costs in the cloud is pretty straightforward. You need scale to zero and you need more density. But how to achieve these goals is where the challenge is. So to have a successful scale to zero strategy, you need your applications to start up very quickly. If you have slow startup times, that's going to be noticeable if you're scaling from zero. If it takes a few seconds to start up, that's a noticeable lag that your end users are going to notice. So this is important, especially if you have JVM app-based servers, that you need to configure them to start up quickly. Equally as important is how much memory you're using when you're all running, especially true for apps that are memory-bound and not CPU-bound. If you can squeeze in your applications into fewer containers, then you're spending less to run your application. So tuning your JVM to minimize memory requirements is very important. So in this presentation, I'm going to demonstrate a few JVM technologies that you can use to help save costs as you deploy your applications to the cloud. Right, so what can we do to improve JVM startup? So I'm going to show you a few solutions that are currently being looked at in the industry. Some have been around for some time, some are fairly new, and I'm going to discuss some of the pros and cons of each one. So the first approach to improving startup time is class metadata caching. So if you're familiar with app CDS in the hotspot or in J9 shared class cache, it's basically an approach where you save the internal state of a Java class and reuse it on a subsequent run. So in OpenJ9, it saves the the internal representation of the class to a file. And then in subsequent run, you don't have to rebuild the class from the beginning. You start from an intermediate state. And so there's a much shorter path to getting the class ready. So the effect is that it improves class loading time, which improves startup time. So the benefits of this approach is that it's probably the easiest way to get a startup boost. You just enable it and that's it. With OpenJ9, it's a simple command line option. I think we actually enable it by default now, so you get it for free. There may be some code changes required if you're using a custom class loader, and the changes themselves are fairly trivial. If you're not, then there are no code changes required, and it just works. And it's the same JVM you're using, so it's everything just works as intended. The drawbacks are that the startup gains are relatively modest in comparison to some of the other approaches that I'll show you. So, with an app server like Liberty, we can start up under a second, around the 900 millisecond range, which is pretty good, but we'll see how you can start even faster with other approaches. Right, so the next one is static compilation. So, a big chunk of the time taken to start up an application is class loading. And so if you statically compile your application, basically you don't have to run static initializers at runtime. Everything's just baked in to the generated image. So with static compilation, you essentially avoid all of these startup costs, and once you start the application, it just goes. So, I think the most popular example now is native image, Growl native image, if you're familiar with that. There's another project that I believe Red Hat's working on called CubicCC. Similar thing, it's a Java static compiler, generates a native image. So the benefits of this approach is that you can achieve very fast startup times. With Quarkus native image, you can start under 100 milliseconds, which is very fast. Another benefit is that because you're doing static compilation, the compiler has full knowledge of what's going into the image, and it can strip out the parts of the application that aren't needed. So your on-disk footprints get smaller. Now, the drawbacks are kind of related to some of the benefits. Because you are only putting what you need into the application, it kind of limits the dynamic capabilities of the JVM. So things like dynamic class loading, reflection, there are some limits to what you can do with that. You have to make sure that the compiler knows at compile time what class you're going to need, what methods you're going to reflect. Everything has to be known to the compiler. So if your application is relying on being able to just download a jar and run it, then you may have to redesign your application. And it's not just your application; it's your dependencies as well. Everything you depend on needs to be able to work with native image. So for these reasons, this approach tends to work better for new applications. If you're writing an application today, like starting now, then this approach works better. But if you have an existing application and you want to migrate it, then it can be challenging. Some other drawbacks are that it has very long build times because you are compiling a native application, so it's inherent in that process. And the peak throughput is not as high as it would be with the JVM. So the static image just has all the code compiled, whereas a JVM has a dynamic compiler, a JIT, that uses runtime profile information to optimize the code. So peak performance is higher with a JVM because you just have more information at runtime. And so there are limits to the amount of throughput that you can get in comparison with a traditional JVM. And because it's a native image, the debugging tools that you're probably using won't work because those are tools for JVMs. You need to use things like GDB if there's a problem. So these are kind of the things you have to weigh when looking at this approach. All right. So third approach, and this is what I'm going to focus on today, is checkpoint restore. So essentially, the JVM is run to a certain point before the application is ready to take requests. It's stopped, it's checkpointed, so it's frozen, it's saved, it's serialized to disk. And then when you need to deploy it, you resume the application. So essentially, the saving is that you don't have to rerun that startup phase, you just resume from when it's ready. So the benefits of this approach are that you get very fast startup times. You can get around the 100 millisecond range, depending on the application. And because it's still a JVM, there's no limits to peak performance. You still have the JIT, the dynamic compiler, that's still optimizing the code at runtime. So it's the same JVM, but you get faster startup time. Now, the drawbacks are that you do require code changes. So your application has to request the checkpoint. So the code change is required, and there may be other code changes required to reinitialize state after the checkpoint, just to reinitialize connections that you may need, and things like that. But overall, in the examples we've looked at, we expect that these changes are less than what you'd have to do with a static compilation approach. So essentially the goal of this approach is to achieve something in between static compilation and class metadata caching. So we want the same startup performance of static compilation, but we want all the capabilities that you would get with a normal JVM. So essentially we're trying to get the best of both worlds here. All right, so in order to checkpoint the JVM, we need a mechanism that can suspend the state and serialize the process, then resume it at a later time. So it is possible to do this in the JVM. However, there's a considerable amount of work required to track OS resources. The OS is very involved in this process, so the OS is actually the best place to do this. And so what we've been doing is we've been using a Linux utility called CRIU, checkpoint restore in user space, and that's basically how we've been leveraging this capability from the JVM to do checkpoint and restore. So CRIU is a project that began in 2012. It actually started earlier, but at that time it was a kernel space project. In 2012 is when they decided to do it in user space. So it's a utility that can take a running container or individual application and then checkpoint its state, suspend it, serialize it, and then that suspended state has everything you need to resume it. So the state can be resumed on the same machine or on a different machine, so it's quite flexible. So how does it actually work? So an application, when you run an application, it makes use of system resources, so like files, memory, C groups, maybe namespaces. So at checkpoint time, CRIU queries the kernel for all the OS resources that the application is using in order to determine the state of the application. So, all the memory pages, file handles, etc. And then it uses a system called like ptrace to observe the application and take control of execution. And then once it's gathered all the information, it writes it out to a file. And then at restore time, it replays all the system calls that we used to create that initial state so that you get back the application as it was just before the checkpoint. And then you map back in the memory, map back in the register values, and then you just resume. So it's a bit of a simplification, but overall that's kind of the high-level idea of how it works. So CRIU was originally intended for live migration, but as you can see, there's many use cases, and the one that we're most interested in is boosting application startup time. So at OpenJ9, we've developed a feature called CRU support that offers CRU capabilities to Java developers. So a little quick note about OpenJ9. So OpenJ9 is an open source JVM. It's part of the Eclipse Foundation. It was open sourced in 2017, but it's based on the IBM Java VM that's existed for over 20 years. So it was just made open in 2017. There's the commercial offering is called Semaru, but it's the same underlying technology. So OpenJ9 CRU support is a feature that lets users take advantage of CRU capabilities. But it's more than just an API. It's also built-in JVM support to make the whole process of using CRU much more seamless. And we'll take a look at that in a bit more detail. So here's a little illustration of what the API looks like. So it's fairly simple. It uses a builder pattern to set up the CRU support instance. And then the methods at the top are to query support for CRU on the machine. In the middle are methods that modify how the checkpoint is taken. So a lot of the ones in the middle are just essentially wrappers to CRU calls. And then at the bottom are some of the methods to leverage JVM support. So when you take a checkpoint in one environment and you want to restore it in another, there are many incompatibilities that may arise between the two environments. For example, if you have two CPUs in one 4 CPUs in the other, if your application is sensitive to the amount of processes you have, there may be a need to compensate for these differences. So there are hooks that are provided to users to address those differences. And the JVM itself has built-in hooks that compensate between those differences as well. And then at the bottom, you just call checkpoint JVM to initiate the checkpoint process. Okay, so let's just look at the workflow. So in a typical application run, you've got the JVM startup, so initializing the JVM, initializing DLLs, et cetera. And then you have to load the JCL, initialize those classes. And then once that's complete, you have to load the application classes and do the initialization there. Then once all of that is done, your application is ready. So here's a visual representation of what that looks like. These boxes are not necessarily to scale, but you get the idea. So with CRU support, the way you use the API is essentially you want to, when you're building your application, let's say you're deploying your application via containers, you would want to do the checkpoint run as part of your container build. So you would initiate the checkpoint after the application is ready, but before it connects to a database or is ready for external connections. And so you've built in a ready application within your container. And then at deployment, all you do is you use the CRU utility to restore that image, and it just continues. And so that's the benefit of this approach, is that there's a much shorter path to the application ready state. So this is how you get the big startup boost with CRU. So yeah, this time let's look at a short demo just to see how this works. So, okay. All right. So prepared a little Hello World application. I can make that a little bigger. So it's a pretty simple application. It's just going to print start, and then it's going to sleep for a few seconds, and then it's going to print application ready, and that's it. Oops. Get a better look at what's going on here. Okay, so let's just compile. All right, so that printed start. We're just simulating what an application would do. So let's see how long it takes. All right, so it took 3 seconds, just as we expected. So now let us do a checkpoint and restore. All right, hope you don't mind my tabbing. So essentially what this is going to do is it's going to create a series support instance, and we're going to tell it to not keep running after creating a checkpoint. So that's what this first option does. We're going to tell it that it is being launched from a shell job. So that tells CRU that the parent is the bash process. So don't dump the entire process tree, just dump the application. And then the JVM uses file locks, so we're just notifying CRU that that will be needed. And then the rest are for logging. And at the end is the checkpoint JVM. Okay, so let's compile that. And then I have to make my directory to put the checkpoint data, and then ready to launch the application. Right, the one thing I'm missing is, so we don't enable this feature by default. You have to enable it with a command line option. So that's that there. Plus. All right. So yeah, so I ran the application, and then that message killed, that's from CRU itself, just saying it's stopped the process. So the next thing to do is to restore the application, and I always forget the command, so I'm just gonna copy it. And there we go. So we've restored the application. Let's just, right, so that's, we can't really tell that. I think that's 78 milliseconds. Yeah. So you can see, you can get pretty fast startup gains with this approach. So what we looked at was basically a toy application. It's not really doing much, but you can kind of see how this can improve startup time. So the next thing we're going to look at is with a real app server. We're going to use Liberty. So Liberty is an open source Java runtime designed for cloud native development. Essentially, it's a framework for building web services. So it supports microprofile and Jakarta EE. So Liberty makes use of OpenJ9 to support CRU capabilities. And so we're going to take a look at how that works. All right. Okay, so I set up a server earlier, so we're just going to run it and start and see what it looks like. All right, so just a simple page that's not really doing much. So the important thing here is how long it took to start. So we see here it took 3.9 seconds, I think. So now we're going to use the instant on feature. That's what it's called in Liberty. That makes use of CRU support. So what we do is instead of doing a run, we do a checkpoint, and then we tell it at which phase we want to do the checkpoint. Right, okay, so the message there also from CRU telling us that it has stopped the application. So then we'll do a run again. And we can see here it started up in around 260 milliseconds. Let's just make sure our page is still there. Yeah, everything's good. So you can see that it's roughly, maybe 18x improvement. So that's the kind of improvement you can get with this approach. So yeah, so here are just some performance numbers that we've run with instant on and without instant on. So for the most part, typically you can expect around a 10x improvement when you use the feature, but it can vary a little bit depending on what your application does. So in the last example, we were using Liberty to do the checkpoint and restore. And you may have noticed that I chose a specific phase to do the checkpoint at. So the way Liberty works is that the first thing it does is it starts the kernel, loads features, processes them, then it starts the application processing. And then, after that, it's done the deployment phase. And then after the deployment phase, it starts the application. And then basically everything before the application receives requests is the application's phase. So essentially, in order to get the most benefit from this, you need to take the checkpoint as late as possible. So in the example I showed there, I did it at the applications phase, which is the latest possible point to take the checkpoint, and that's what we saw, the improvement we saw. If I had done it at an earlier phase, it would not have been as, the start time would not have been as fast. So, clearly you want to do it as late as possible, but the later you do it, the more complexity there is. So the later you take the checkpoint, the more state you have built up in the JVM, and the more potential for incompatibilities with the restore environments. And some of these things could be, certain APIs are time sensitive. And so if you took the checkpoint at time 1, restore it at time 2, then, maybe if your algorithm is sensitive to that change, there might be an issue there. So at OpenJ9, we've added some support to mitigate these issues. So we have automatic fix-up of a lot of these APIs so that these differences don't cause an issue when you're using this. Okay, so now we're going to look at ways to improve JVM density. So before we get into that, we're going to review some basic JVM components. So that's the JRE, the Java Runtime Environment. Basically everything you need to run your code includes the JVM and the JCL. The JCL offers basic functionality like all the packages and classes that you're familiar with. And then in the JVM, there's the JVM is essentially the computing machine that runs the bytecodes. And it's composed of natives. These offer the low-level system functionality that is required by the class libraries. And then you've got the class loader that loads the classes, links them, verifies them, etc. And then you have the interpreter responsible for executing the bytecodes, the JIT that dynamically compiles the bytecodes and turns into the machine code. And then the GC, which is basically the memory manager responsible for memory allocations and recycling memory. And then at the bottom is the port and threading library, which is the abstraction layer over the platform-specific APIs. So just a very quick overview. So now we're going to look at the main contributors to JVM footprints. So the main things that contribute the memory that the JVM uses up. So the first is classes. So classes is a very big contributor. The Java heap, native memory as well. and the JIT. Now, there are other contributors like the Java stack, trace or logging info, but these tend to be relatively minor compared to these four. So for classes, there are things you can do to minimize the memory that this consumes. So earlier I talked about the shared class cache feature and how that can be used for startup improvements. But this can also be used to improve footprint as well. And so we're going to take a quick look at how that works. So in OpenJ9, when a class is loaded, OpenJ9 separates the class metadata into read-only and writable components, as shown in this picture. So the ROM is the read-only, the RAM is the writable. And the main distinction is that the ROM captures the immutable state of the class, so things like bytecodes, constants, string literals, things like that. And the RAM captures the live state of the class, so resolution data, anything that is, sensitive to options that you may have passed in. So the ROM part tends to be consistent. Every time you load that same class, you're going to generate the same ROM class. But the RAM part will vary depending on how your JVM is run. Now, another thing about the ROM part is that it is position independent. It doesn't use any direct pointers. It uses relative addressing. So it doesn't matter which address space it's in, it's still sane. So in this example, we have 3 JVMs running code. They may be running the same code, may be running different code, but for the most part, there's going to be a substantial amount of overlap in the classes that they load. So you can think of running a few instances of the same microservice or something like that. So when you load a class, it first gets translated into a ROM class, then a RAM class, and then it's ready. So the 3 things to consider, the conversion from your jar file to something you can use at runtime takes time. It doesn't happen instantly. And in the case of ROM classes, the result is always the same. And so that means that there's an opportunity to share it. So essentially, the shared class cache feature is a feature where the first time you load a class, you write it into the cache. And then when the next time you run the JVM, or if a different JVM comes along, it queries the cache to see if the class exists. And if it does, it uses the class in the cache. And so that's where we get the startup improvements, but also you can get footprint improvements because now you're sharing part of the class metadata between multiple JVMs. And so you're shrinking your footprint. So we've seen in cases where you've got a few instances sharing using the same class cache, you can see up to 20% improvements of footprint. Okay, so next is the Java heap. So Java heap, of course, is where most of the object allocation occurs. So the heap can be configured, like the size of the heap, the heap limits can be configured so that it restricts the heap expansion. And this could be a way to reduce your footprint. However, this does come at a cost of throughput. So if you restrict the heap, that means you have to, potentially you have more GC cycles occurring because you have to reclaim memory more frequently. And so if this is a trade-off that you can tolerate, then this might be another way to decrease footprint. The next is native memory. So in this case, there are not many solutions to address this. And that's because it's typically driven by application behavior. So think of direct byte buffers or unsafe memory allocate. This is what that category is made up of. You can use options like -XX max direct memory size to restrict the amount of memory you'll use. But again, all this, in some cases, all this might do is mean you hit a out-of-memory exception. So in this case, there are less options to address this beyond changing the application. The fourth thing you can do is to configure the JIT to drive more AOT compilations, which can be shared between multiple JVMs. The JIT can also be configured to be more conservative with inlining and recompilation. So with less inlining, your code cache is smaller. With less recompilation, there's less code you're putting in the code cache. So all of these things reduce the footprint. But again, this also comes at a cost of throughput. So if that is a trade-off you can make, then this is a worthwhile approach. Now, most JVMs are configurable, so you can tune these components to meet your needs. OpenJ9 is no exception. There's a lot of knobs to tune it. However, if you're not familiar with the JVM specifics, it can be difficult to figure out which knobs to tune to get the desired effect. So at OpenJ9, we've introduced a new option. It's actually been out for a little while now. It's called Xtune Virtualized. And essentially, this option is geared towards resource-constrained environments. So it modifies the JVM to reduce the amount of CPU consumed as well as the memory footprint. So it modifies the internal JIT heuristics to lower compilation time, so it's not stealing as much CPU that the application needs. It does cheaper compiles, less inlining, more conservative with compilations. So all this means is smaller code cache, less use of JIT scratch space. And so in some cases, you can see a footprint reduction of about 25%. Now, there is a side effect that, if you're doing less compiling, it's going to affect throughput. But we've seen this to typically be less than a 5% reduction in throughput. This option also turns on another feature called GC idle detection, which puts the JVM in a mode where it can trigger a GC when it's idle. So basically, the JVM detects what the threads are doing, and if it detects that they're all idle, then it will trigger a GC, which will do a full heap compaction. And then on top of that, it's going to disclaim any unused memory pages. And so that minimizes the RSS. Now, there's another feature that kind of takes this to the next level. So previously, I talked about shared class cache. It allows you to share class metadata with multiple JVMs. And it also allows to share AOT compiled bodies. This is kind of taking that idea to the next level. So on the left here, you can see 3 typical JVMs. Each one has a JIT. If you're deploying many applications, similar applications, each of those JITs is going to compile the same methods over and over again. And likely the result is going to be the same over and over again. So the idea of JIT server is basically to decouple the JVM from the JIT. And so what you have on the right is you've got a JIT server and you've got client JVMs. And so when the JVMs need to do a compilation, they request to the JIT server. So this has many benefits, as we'll see. So the first benefit is when you're provisioning in a system like this, you don't need to take into account the transient memory spikes that can occur from JIT compilation. You basically size your containers for what they will need at steady state because the JIT server is going to do all the compilation. So it's got a much more predictable resource usage. From a performance perspective, because the JIT is no longer doing compiles in the node, it's not competing. You don't have the JIT competing with the application for CPU. So it's a much more predictable performance characteristic. Additionally, if you make a request to the JIT and the JIT has already compiled that method before, you just get it. So there's, some cases there's no compilation time. So in a lot of cases, we see that ramp-up time gets a lot faster as well. And finally, it's just added resiliency. By decoupling the JIT and the JVM, if there's a problem in the JIT, it doesn't bring down the JVM. You can revert back to local compiles. So with this approach, if the JVM loses connection with the JIT server, it just compiles locally. It doesn't cease to compile. So here is a little diagram that kind of illustrates the workflow. So on the left, we've got the client JVM, and on the right, we have the JIT server. And so basically, when you need to make a compilation request, first check to see your cache, if it's there. If it's not there, check to see if you have connected to a JIT server. If you have, then you ask the JIT server the same questions. Is it in the cache? If it is, you just return the method. If not, then you do the compilation, and then you return that. And then once it gets to the client's JVM, you populate the cache, and then you can execute the method. So yeah, we can do a quick demo to kind of see how this works in practice. So in this demo, there are going to be 3 microservices, so 3 WT-Acme servers. They're all configured differently. So the first one is configured with 400 megabytes, the second one with 200, and the third one with 200, but that one is connected to a JIT server. And then we'll just output the results to Grafana. So let's give that a try. Just here. Okay. So the first thing I'll do is start. Start influx. Clean everything. Okay, so I'll start the MongoDB server. And I will start Prometheus. Then I will start the JIT server. And I think we'll be able to get some metrics. Oh, there we go. Okay, so it's noticed that the JIT server started. Now there's no connections yet. So yeah, number of connections, 0. It just has one compilation thread that's idling, just waiting for a request. And then we've given it 1 gig of memory and no CPU utilization. So now let's start some Acme Air servers. And let's run some load. So we started the 3 servers. So the first one, again, it's got a higher memory limit, 400. Second one has 200, and the third one has 200. But this one has different options. So this one is connected to the JIT server, and these are just the options to say where to find it and which port to connect to. So yeah, so we can see the JIT server is connected. We saw a spike in CPU utilization, and that's just because it's in compilation. And this is good. It means, the more work the JIT server does, the less that has to be done in the client nodes. So it ramps up the number of JIT threads, and I guess it must be done most of the compilation because it's back down. So let's take a look at the worker nodes. Okay, so at the top here is the 400 megabyte node. Here is a 200 meg node, and here is the 200 meg node connected to JIT server. So you can see that if you compare the 200 meg node connected to the JIT server with the one that isn't, you can see that the ramp up is much faster than the one without JIT server. And that's just because when you're restricted with memory, you don't have as much scratch space to do compilations. You have to be more conservative. And so that is going to affect your ability to your throughput, essentially. So on the y-axis is the ops per second. So in comparison to the one that isn't constrained, you can see here that it has the same throughput as the one with half as much memory, but even then it got there a lot slower. So you can see that with JIT server, your ramp up is faster, and you can achieve the same performance as you would in an unconstrained environment. Okay. Oops. All right, so yeah, in that example, we saw how JIT server can be used to improve ramp-up time. But more importantly, for the purposes of this presentation, it can also be used to improve density. So in this example, we have two configurations. The one at the top has 3 nodes, and the one at the bottom has 2 nodes. Now, they're doing the exact same thing. So there's a legend at the bottom right that explains what all the microservices are. The difference between the two configurations is that the configurations at the bottom are sized 150 to 250 megs smaller. And that's because when the bottom one is using a JIT server, so you don't need to size the nodes to account for that. So overall, what you see is that the total memory usage between the first configuration and the second one is about 6 gigs less, so it's a 30% improvement. And the peak throughput between both configurations is identical. So it's kind of it's a good example to show the benefit of JIT server and how this can bring real savings from a cloud cost perspective. So here, this chart kind of shows the benefit of JIT server in constrained environments. So in all these cases, they're running the same thing. The first one on the left, the node is provisioned with 512 megabytes. So you can see that the ramp up is faster with the JIT server than it is without, which is one of the benefits of this approach. But overall, peak throughput is the same with both. Now, as you start to constrain the amount of memory the node has, you start to see a difference between peak throughput with JIT server and without. And if you constrain it more, the relative difference gets larger and larger. So that kind of demonstrates some of the benefits of this approach. So when is it optimal to use JIT server? Basically, because you're doing remote compilation, you need to communicate back and forth with the JIT server. You have to make the compilation request. Then the JIT server may need more information about the application. This approach works well when you have low network latency, so under a millisecond is best. When the latency goes up, then you'll start to see it become an adverse impact because of the back and forth communication that's required. If the application is running in a resource-constrained environment, then this approach works very well. Also, if you need to do many compiles in a relatively short amount of time, so if you need to scale out you need to spin up many instances, and they all need to do compiles. This approach is great because once you've compiled it for one, you can just return it for the others. Right. So yeah, in conclusion, this talk we've looked at a few ways to improve density. So with JIT server, but also with things like class metadata sharing, and also ways to improve startup time. And essentially, with the right tools, you can make deploying to the cloud a lot cheaper. So here are some resources. So all the technologies that I've demoed today, there are links to all of those. And there's more examples there as well if you need more information. And yeah, this concludes my talk. Any questions?
Does your underlying Java version matter?
So can you repeat that?
Your application Java version, does it matter?
So for some of I'll repeat the question. Does the version of Java matter? For some of the applications I demoed, so for JIT server it doesn't. It's supported from 8 all the way up. For the series support version, it's only supported 11 and up. We have plans to backport it, but we're not at that point yet. So some features aren't available in all Java versions. Yeah. All right, if there are no more questions. Oh, there's one more.
Yeah, for creating JVM checkpoints, have you tried with anything as complex as, say, like Spring or Spring Boot? Do you have any guidance on that?
So we haven't tried Spring or Spring Boot. We have tried Liberty, which is probably the comparable example. And for the most part, it wasn't too complex. We had to add a few hooks in the JVM to support that, but I think we've captured all those use cases. Thanks. So yeah, thanks everyone for joining my talk.